There is water on the moon, not just a little. Not just some faint chemical trace locked inside a mineral grain. Water. Real, actual water ice, sitting in the darkness beneath the lunar surface, waiting. And the story of how we found it, the mission that confirmed it, and what it means for everything that comes after, is one of the most extraordinary things NASA has ever done. And they summarized the whole discovery in a single sentence. One sentence. We are going to spend a lot of time unpacking that sentence today, because behind those few words is a story that goes back decades, involves some of the most creative engineering NASA has ever attempted, and ends with a spacecraft deliberately crashing itself into the moon at 2.5 kilometers per second. If you are the kind of person who finds that interesting, stick around. And if you want more stories like this one, hit subscribe now, because we go deep on the science, the missions, and the mysteries that most people never hear about. Let us start from the beginning, because to understand why the LCROSS mission mattered so much, you need to understand the question it was trying to answer, and why that question had been driving scientists absolutely crazy for the better part of a century. The moon looks dry. That is the obvious thing. You look at it through a telescope, you see craters and dust and gray rock, and nothing about that picture suggests water. When the Apollo astronauts brought back samples in the late 1960s and early 1970s, those samples were bone dry, drier than anything found naturally on Earth, drier than the driest desert. The scientists who analyzed those rocks concluded that the moon had no water to speak of, and for a while, that was that. Case closed. The moon is dry. Move on. But then something started to nag at the edges of that conclusion. It started with a question that sounds almost too simple. The moon has no atmosphere, no weather, no erosion, no geological activity of any significance. It is, in many ways, a museum, a place where things that happened billions of years ago are still sitting exactly where they landed, untouched, perfectly preserved. And one of the things that has been hitting the moon for billions of years is comets. Comets are made of ice. That is not a controversial statement. When a comet falls into the inner solar system and gets close to the sun, the ice vaporizes and streams off behind it, creating the tail that makes comets so beautiful and so visible from Earth. Comets are, at their core, dirty snowballs. And billions of them have hit the moon. So the question becomes, where did all that water go? On Earth, if a comet hits, the ice vaporizes, the water enters the atmosphere, gets distributed around the planet, cycles through the oceans, and ice caps, and rivers, and living things. The water stays, it just moves around. But on the moon, there is no atmosphere to catch it. When a comet hits the lunar surface and the ice vaporizes, most of that water is going to escape into space. Most of it. But not necessarily all of it. Here is where it gets interesting. The moon has no axial tilt to speak of. Earth is tilted about 23 degrees relative to its orbit around the sun. That tilt is what gives us seasons. It is also what means that every place on Earth gets at least some sunlight throughout the year, even if it is just a few hours in winter. The moon, by contrast, is tilted only about 1.5 degrees, which means there are craters near the lunar poles, deep craters with steep walls, where the sun never shines. Not just seasonally, not just occasionally, never. Not in billions of years. These are called permanently shadowed regions. And in permanently shadowed regions, temperatures drop to around -240 degrees Celsius, maybe colder in some places. These are among the coldest spots in the entire solar system, colder than the surface of Pluto, colder than almost anything we have ever measured. And if even a tiny fraction of the water vapor from a comet impact drifted down into one of those shadowed craters before it could escape to space, it would freeze instantly and stay there, for billions of years, completely undisturbed, sitting in the dark. In theory, these shadowed craters could be cold traps. They could have been accumulating ice for the entire history of the solar system, collecting a little bit at a time from every comet and asteroid impact, from the solar wind, from volcanic outgassing early in the moon's history. Over billions of years, even a tiny drizzle adds up. That was the theory. That was what some scientists had been arguing about since the 1960s. And for decades, nobody could prove it one way or another, because those craters are in permanent darkness, and there is no way to see inside them from Earth. The first real hint came in 1994, from a spacecraft called Clementine. Clementine was a joint mission between NASA and the Ballistic Missile Defense Organization, which sounds like an odd pairing for a lunar science mission, but that is a whole other story. Clementine was actually designed primarily as a technology demonstration for missile defense sensors. The moon was almost an afterthought, but while it was up there, scientists used it to bounce radar signals off the lunar surface and measure the reflections. Water ice reflects radar in a very distinctive way. It produces what is called a circular polarization ratio anomaly, which is a technical way of saying that the radar signal bounces back in a way that is consistent with ice. And Clementine found that signature near the lunar South Pole. The scientists who analyzed the data were cautious but excited. They said it was consistent with the presence of water ice. They did not claim certainty, but the hint was there. Then in 1998, NASA sent a spacecraft called Lunar Prospector to orbit the moon and measure its surface composition. Lunar Prospector carried an instrument called a neutron spectrometer, which works on a beautifully simple principle. When cosmic rays from space hit the lunar surface, they knock neutrons loose from atoms. Those neutrons scatter upward, and the spectrometer detects them. But if there is hydrogen in the soil, those neutrons slow down. Hydrogen is very good at absorbing the energy from fast neutrons, which is why nuclear reactors use water as a moderator. So if Lunar Prospector saw slow neutrons coming up from the surface, that was a sign of hydrogen. And if there was hydrogen near the poles of the moon, in the permanently shadowed regions, then the most logical explanation was water. Lunar Prospector found exactly that. A clear, unmistakable enhancement in hydrogen near both poles, but especially near the South Pole. The signal was strong. Something like 1 to 3% water by mass was the estimate. For every 100 kilograms of lunar soil in those regions, there might be 1 to 3 kilograms of water ice. That sounds like a small number. But when you multiply it across the area of all the permanently shadowed regions near the South Pole, you start talking about billions of tons of water ice. Billions of tons. The scientific community got excited, then cautious, then frustrated, because while the neutron spectrometer data was suggestive, it was not proof. The instrument could detect hydrogen, but it could not distinguish between water ice and other hydrogen-bearing compounds. Maybe it was just hydrogen atoms embedded in the soil by the solar wind. Maybe it was hydroxyl groups attached to mineral grains. Maybe it was something else entirely. The signal was there, but what it was pointing to was still unclear. And here is where the mission planning started to get creative. The most direct way to find out what was in those craters was obviously to go look. Land a spacecraft in a permanently shadowed region, drill into the ground, take a sample, analyze it. Simple, also enormously expensive, technically challenging, and extremely risky. You are talking about a place with no sunlight, which means no solar power, which means batteries or nuclear power, which means a much more complex and heavier spacecraft, which means more expensive launch, and so on. The engineering challenges compound on each other rapidly. What scientists wanted was a way to get the material out of that crater and into the sunlight where it could be observed. What they needed was an explosion. If you could hit one of those permanently shadowed craters with something big enough and fast enough, the explosion would throw a plume of material high above the crater rim, up into sunlight, where a spacecraft flying through or above it could analyze what was in it. Dust, rock, and if the theory was right, water vapor and ice crystals. The concept had actually been considered for Lunar Prospector. When that mission ended in 1999, someone pointed out that the spacecraft had a little bit of fuel left and was about to deorbit anyway. Why not aim it at a permanently shadowed crater, crash it in and see if any observatories on Earth could detect water vapor in the ejecta plume? They tried it. Lunar Prospector hit the lunar surface on July 31, 1999, at a speed of about 1.6 kilometers per second. Every telescope available was watching. Ground-based observatories, the Hubble Space Telescope, anyone who could point something at the moon that night was pointed at the moon. Nothing. No detectable water vapor. No signal. But nobody was ready to give up. The failure of the Lunar Prospector crash was not necessarily because there was no water. The spacecraft was simply too small. It was only about 150 kilograms. At that impact speed, the energy released was not enough to throw a detectable amount of material high enough to be observed from Earth. The plume was too small and too brief. What was needed was something bigger. Enter LCROSS, the Lunar Crater Observation and Sensing Satellite, pronounced by the people who worked on it as LCROSS, which rhymes with across. The mission was proposed as part of the new wave of lunar exploration that NASA was launching in the mid-2000s, riding the ambition of returning humans to the moon under the Constellation program. If people were going to live and work on the moon, one of the most practical questions was whether there was water there. Water for drinking and for agriculture, but also, critically, water that could be split into hydrogen and oxygen, providing rocket propellant. If the moon had water, it could potentially serve as a refueling station for deep space exploration. The question was no longer just scientific, it was strategic. LCROSS launched on June 18, 2009, together with the Lunar Reconnaissance Orbiter, or LRO. They shared a ride on an Atlas V rocket, which was the beginning of a beautiful partnership, because LRO would go on to provide some of the most important context for the LCROSS results. The two spacecraft separated after launch, and LRO went into a low polar orbit around the moon to begin its detailed mapping mission. LCROSS, meanwhile, did something unusual. Instead of heading straight to the moon, it went on a long, looping path that took it out to nearly 400,000 kilometers from Earth, in an orbit designed to give the mission controllers time to calibrate their instruments and select the best possible target crater. This extended cruise phase lasted about 3.5 months. The target they eventually chose was a crater near the lunar south pole called Cabeus. Cabeus is about 98 kilometers in diameter, which makes it a fairly large crater, but more importantly, radar and neutron data both suggested it had a higher than average concentration of hydrogen. If water ice was anywhere, Cabeus was a good bet. Now here is where the engineering of this mission gets genuinely elegant in its simplicity. The original plan was to buy a separate impactor spacecraft, something large and heavy, to crash into the moon. But budget constraints forced the mission designers to get creative. What they had was the Centaur upper stage rocket that had launched LCROSS and LRO into space. Once a Centaur finishes its job of pushing the payload on its way, it is normally just discarded. It becomes space junk. But the LCROSS team had a different idea. What if they kept the Centaur and used it as the impactor? The Centaur upper stage weighed about 2,300 kilograms. That is more than 10 times the mass of the Lunar Prospector spacecraft. And it was going to be traveling at about 2.5 kilometers per second when it hit. The kinetic energy in that impact would be enormous, equivalent to roughly 2 tons of TNT exploding on the lunar surface. That was enough to throw a significant, detectable plume of material high above the crater rim. So the LCROSS shepherding spacecraft would trail behind the Centaur at a distance of about 250 kilometers, watching the Centaur hit, flying through the ejecta plume, analyzing everything it could detect in the 4 minutes it had before it, to hit the surface. LCROSS itself would then become a second impactor, throwing up a second, smaller plume that could be observed from Earth and from the Lunar Reconnaissance Orbiter. The spacecraft carried 9 instruments: an ultraviolet spectrometer, a near-infrared spectrometer, a mid-infrared camera, a visible camera, a near-infrared camera. The combination of these instruments was designed to detect and characterize whatever was thrown up in that plume: dust, rock, minerals, and, hopefully, water. The mission cost about $79 million. In the world of planetary science missions, that is extremely cheap. This was lean, creative, and ambitious science on a budget that most missions would barely use to develop an instrument. Impact Day was October 9, 2009. The impact site was in permanent darkness, as expected. The time was 11:31 UTC for the Centaur impact. The entire world, or at least the part of the world that was awake and paying attention at that hour, was watching. And then something unexpected happened. A lot of people expected to see this huge, dramatic explosion visible through a backyard telescope. NASA had been publicizing the event, encouraging amateur astronomers to watch. Night sky enthusiasts had set up cameras. Live streams were running. People were genuinely excited. The Centaur hit, And from Earth, the plume was nearly invisible. Not because there was nothing there absolutely was. But the plume, while enormous on a lunar scale, was small on an astronomical scale. The crater rim blocked much of the view from Earth. The plume rose to about 10 kilometers above the surface, which sounds impressive, but the Moon is nearly 400,000 kilometers away. The geometry simply did not cooperate for Earth-based observers. Social media, which was already a significant force in 2009, lit up with people complaining that they had seen nothing through their telescopes. A lot of headlines the next day were variations of NASA crashes rocket into Moon and nobody sees anything. But LCROSS saw everything. The shepherding spacecraft was right there, 250 kilometers away, heading straight toward the impact site at exactly the right angle, with all 9 instruments running at maximum sensitivity. For 4 minutes and 16 seconds after the Centaur impact, LCROSS flew through the ejecta plume and the vapor cloud, measuring and recording everything it could detect. Then it hit the surface itself, and the mission was over. The data took time to analyze. This was not a case of looking at a readout and immediately knowing the answer. The spectral data, the chemical fingerprints left in the light passing through the plume, had to be carefully separated from noise, calibrated, compared against known spectra for different compounds. It took weeks. And then, on November 13, 2009, 35 days after the impact, NASA held a press conference. The principal investigator of the mission, Anthony Colapriti, stood up in front of cameras and reporters and the watching scientific community, and he said something that people who were paying attention will remember. He said, and this is the sentence NASA summarized the discovery with, "We found water, and we didn't find just a little bit. We found a significant amount." Now, some versions of this story focus on a slightly more formal summary, and the one that gets quoted most often in the literature, the one that NASA put into their official mission summary, was essentially this. The LCROSS impact revealed that water ice exists in the permanently shadowed regions of the Moon. One sentence. That is the sentence. And it is one of the most consequential sentences in the history of planetary science, because it changed everything. Let us talk about what the data actually showed, because the details are extraordinary. The ultraviolet spectrometer on board LCROSS detected the spectral signature of hydroxyl, which is a fragment of water. When water is broken apart by ultraviolet radiation, it produces hydroxyl. Seeing hydroxyl in the plume was a strong indicator that water had been present in the impacted material. But the near-infrared spectrometer went further. It detected the direct spectral signature of water ice. Not just hydroxyl, not just a proxy, water itself. The amount detected in the plume was roughly 95 liters of water vapor and ice in the immediate ejecta cloud. But that number alone is almost meaningless without context. What you really want to know is the concentration, how much water ice is in the soil of Cabeus crater, and the analysis of the LCROSS data suggested that the concentration was about 5.6% by mass. 5.6%. In the permanently shadowed region of Cabeus, for every kilogram of lunar soil, there was roughly 56 grams of water ice. That is better than some of the driest permafrost on Earth. It is vastly more water than the most optimistic pre-mission estimates had suggested. The cold trap hypothesis had not just been confirmed, it had been confirmed spectacularly. And water was not the only thing in that plume. The spectrometers detected a whole range of other compounds: carbon monoxide, carbon dioxide, methane, ethanol, ammonia, and a compound called light hydrocarbons. The plume was a chemistry set, a frozen archive of the volatile compounds that had been deposited in that crater over billions of years by comet and asteroid impacts, by the solar wind, by processes we are still working to fully understand. This was not just ice. This was a record of the solar system's history, locked in the permanent darkness of a polar crater, perfectly preserved for billions of years. When LCROSS crashed into Cabeus, it was not just looking for water, it was opening a library. Now let us think about what this means in a few different directions, because the implications fan out in every direction from that single confirmed fact. The first and most immediate implication is practical. Water is heavy, really heavy. 1 liter of water weighs 1 kilogram, and launching a kilogram from Earth to the lunar surface costs, depending on the mission and the launch vehicle, somewhere between $10,000 and $1 million. The exact figure varies enormously, but the point is that water is extraordinarily expensive to bring from Earth to the Moon. If you want to establish a base on the Moon, a permanent human presence, water is one of the biggest logistical challenges. Humans need water to drink, to grow food, to maintain hygiene, and to split into oxygen for breathing. Without a local source, you are shipping it all the way from Earth, which makes a permanent moon base almost impossibly expensive to sustain. But if there is water ice already there, concentrated in the soil at 5% by mass, then you have a local resource. You build a processing facility, you scoop up the regolith, you heat it gently, the ice sublimates into vapor, you capture the vapor, you have water. It is not a simple engineering challenge, but it is not an insurmountable one either. And the economics transform immediately. Instead of shipping water from Earth at enormous cost, you are mining it locally. That local water can then be electrolyzed. Pass an electric current through water, and it splits into hydrogen and oxygen. Hydrogen and oxygen in liquid form are, incidentally, the propellants that power the main engines of many rockets, including the Space Launch System, the rocket NASA is using for Artemis. If you can produce hydrogen and oxygen on the Moon, you can refuel spacecraft on the Moon, which means a spacecraft traveling to Mars or the outer planets does not have to carry all of its propellant from Earth. It can launch from Earth with just enough fuel to reach the Moon, refuel, and then continue its journey with a full tank. The Moon as a fuel depot, the Moon as a stepping stone. This is not science fiction. It was always theoretically possible, but LCROSS turned it from a theoretical possibility into a practical ambition, because now we know the water is there. The second implication is scientific and goes considerably deeper. Where did all that water come from? The simple answer is comets and asteroids. That much seems clear. Comets and water-bearing asteroids have been hitting the Moon for billions of years, and the permanently shadowed regions near the poles have been collecting the volatile fraction of those impacts over geological time. That is the basic model, and it is almost certainly broadly correct. But the other compounds that LCROSS detected in the plume add complexity to that story. Methane, ethanol, carbon compounds. These are not just comet ingredients. They are the building blocks of organic chemistry. The carbon and hydrogen compounds that LCROSS found in Cabeus are very similar to the kinds of compounds found in primitive carbonaceous chondrite meteorites, which are some of the oldest objects in the solar system. The stuff locked in that crater is a frozen sample of the early solar system's chemistry. There is also evidence that some of the water in the lunar permanently shadowed regions might have a different origin. The solar wind, the constant stream of charged particles flowing out from the sun, contains protons. Protons are hydrogen nuclei. When those protons hit the lunar surface, they can interact with oxygen in the soil minerals to produce hydroxyl and, potentially, water. This is a slow process, but over billions of years it adds up. And the distribution of hydrogen around the poles, not just inside the craters but in the broader polar region, suggests that solar wind-delivered hydrogen might account for some of what is there. So the water on the Moon is a mixture. Some of it came from space, delivered by comets and asteroids over billions of years. Some of it might have been produced locally by chemical reactions between solar wind protons and lunar minerals. The cold traps just happened to be the perfect collecting vessels, catching and preserving whatever volatile compounds drifted their way. The third implication is for our understanding of planetary science more broadly. If the Moon has water ice in its permanently shadowed regions, what about other bodies? Mercury, the innermost planet, has almost no atmosphere and barely any axial tilt. It is baked to 450 degrees Celsius on its sun-facing side. But at its poles, in permanently shadowed craters, radar observations have suggested the presence of ice. After LCROSS, those observations became much more credible. The same cold trap mechanism that works on the Moon almost certainly works on Mercury. Ceres, the largest object in the asteroid belt, has been found to have bright deposits of sodium carbonate and, in some craters, what appears to be ice. The dwarf planets of the outer solar system have ice everywhere, but closer to home, the confirmation of water at the lunar South Pole reinforced the idea that the inner solar system, which we tend to think of as dry and rocky, is actually a much more water-rich environment than we assumed. Water gets around, it hides in the cold places, it waits. And there is a much bigger question lurking behind all of this, one that scientists are still wrestling with. Where did Earth's water come from? Earth is covered in water. About 70% of its surface is ocean. Billions of liters of water in the atmosphere, in ice caps, in rivers and lakes and groundwater. Where did all of it come from? The early Earth, freshly formed and violently volcanic, should have been largely dry. The rocks that we're building Earth from were mostly dry silicates and metals. But somewhere, somehow, Earth acquired an enormous amount of water. The leading theory is that it came from the same place the Moon's water came from. Comets and water-bearing asteroids, particularly a class called carbonaceous chondrites, delivered water to the young Earth during a period called the Late Heavy Bombardment, roughly 4 billion years ago, when the inner solar system was being pelted by an intense flux of impactors. The water that delivered life to Earth was carried on rocks from the outer solar system. LCROSS did not prove this theory, but it did provide another piece of evidence that water is mobile in the solar system, that it travels on impactors, that it gets deposited on airless bodies, and that under the right conditions, it can be preserved for billions of years. Every piece of evidence for the water cycle of the solar system adds something to our understanding of how Earth got its oceans. Now let us spend some time on the LCROSS mission itself, because the story of how this mission was designed and executed is worth understanding in full. The team behind LCROSS was led by Anthony Colaprete at NASA's Ames Research Center. Ames has a long history of creative, low-cost missions, and the culture there tends toward the bold and the inventive. When Colaprete and his team were given the problem of confirming water ice on the Moon with a limited budget, they did not reach for the most expensive or technically conservative solution. They reached for the most creative one. The decision to use the Centaur upper stage as the impactor was, in retrospect, inspired. The Centaur is a workhorse of the American space program. It has been launching spacecraft since 1962, and it is a reliable, well-understood machine. Using an expended Centaur as an impactor meant they did not have to build and launch a separate impactor spacecraft. The mass budget, which in rocketry is the single most expensive parameter, was already taken care of. The Centaur was going to be there anyway. The shepherding spacecraft, LCROSS itself, was built on a tight schedule and a tight budget, but it was built well. The team used a combination of commercial off-the-shelf components and adapted instruments to keep costs down. They ran into problems during the cruise phase, including an unexpected fuel leak that forced the team to adjust their operations to conserve propellant, but they managed it. The mission stayed on track. One of the most technically challenging aspects of the mission was getting the geometry right. The Centaur had to hit the floor of Cabeus crater, which is in permanent shadow, at exactly the right angle to throw the ejecta plume straight up and into sunlight, where LCROSS could observe it, and where ground-based telescopes and LRO had a chance of detecting it. The approach trajectory had to be calculated with extraordinary precision, accounting for the Moon's gravity, the exact topography of the crater, and the orbital dynamics of both spacecraft. The impact, when it came, was precise. The Centaur hit almost exactly where it was aimed. The plume rose as predicted. LCROSS flew through it as planned. The instruments collected exactly the data they were designed to collect. For a mission that was improvised in some ways and lean in almost every way, the execution was close to perfect. In the weeks after the mission, as the data was being analyzed, the LCROSS team worked closely with groups analyzing data from the Lunar Reconnaissance Orbiter. LRO had been watching from above and had its own perspective on the impact and the plume. The combination of LCROSS's close-up spectral data and LRO's orbital observations gave scientists a much richer picture of what had happened in Cabeus than either spacecraft could have provided alone. The joint analysis was eventually published in a landmark 2010 paper in the journal Science, with Colaprete as the lead author, announcing to the world what they had found. Water ice confirmed. Multiple other volatile compounds detected. The cold trap hypothesis validated. The south pole of the moon is wet. The paper was followed by a series of additional papers in the same journal issue, each looking at different aspects of the LCROSS data. Together, they represented one of the most complete characterizations of a planetary impact event ever conducted. One of those companion papers, led by Peter Schultz from Brown University, looked at the Centaur impact itself, the mechanics of the explosion, and what it told scientists about the structure of the regolith in Cabeus. What they found was that the plume had two distinct components. There was a flash, a bright hot explosion right at the moment of impact, and then there was a slower, cooler cloud of fine debris that rose over the following minutes. The spectral data from the two phases of the plume were different, suggesting that the water ice and the other volatiles were not uniformly distributed in the soil, but were concentrated at different depths and in different forms. This was important because it suggested that the water in Cabeus was not just a thin surface coating. It was buried, layered through the upper meter or two of the regolith, mixed in with dust and rock, which actually makes sense. Over billions of years of micrometeorite bombardment, the lunar surface gets constantly churned and mixed in a process called gardening. The upper few meters of lunar soil are turned over slowly by this process. The water ice would have been mixed into this churned layer, not sitting on the surface where it would be more vulnerable to destruction by the occasional cosmic ray or ultraviolet photon that might penetrate even into the permanently shadowed regions. The layered, buried nature of the water ice has important implications for any future mission that tries to extract it. You cannot just run a vacuum over the surface. You need to dig. The regolith is actually called lunar soil colloquially, but it is more accurately called regolith, and it is a challenging material to work with. Fine-grained, abrasive, electrostatically sticky, it gets into everything. Designing mining equipment that can function reliably in lunar regolith, in permanent darkness, at extreme cold, is a significant engineering challenge. But it is a challenge that engineers are now actively working on, because the LCROSS data gave them a target. The discovery also had implications for the choice of landing site for the Artemis program, NASA's current human moon program. The Artemis landing sites are clustered near the lunar south pole, specifically because of the permanently shadowed regions and the water ice. The goal is not just to explore the moon, but to demonstrate the ability to use lunar resources. Water extraction is one of the key technologies that Artemis is designed to advance. Without the LCROSS discovery, this strategy might have been less focused, more speculative. With it, the mission has a concrete resource to aim for. There is also a safety dimension to choosing south polar landing sites. The permanently shadowed regions are cold traps for water, but the nearby sunlit ridges near the pole, because of the moon's minimal axial tilt, receive almost constant sunlight. Solar panels on those ridges can generate power almost continuously, unlike mid-latitude or equatorial sites where you have 14-day-long lunar nights to deal with. So the South Pole offers both a water resource and a reliable energy resource within a relatively short distance of each other. LCROSS made the South Pole the most valuable real estate on the moon. Now, a lot has happened in the decade since LCROSS. The story did not end with that one press conference and that one landmark paper. Scientists have continued to analyze and reanalyze the LCROSS data, squeezing more information out of it with improved analysis techniques. New missions have added to the picture, and some of what we thought we understood has become more complicated. In 2020, a paper published in Nature Astronomy reported new results from the Stratospheric Observatory for Infrared Astronomy, or SOFIA, a joint NASA and German Space Agency telescope mounted on a modified Boeing 747. SOFIA detected water on the sunlit surface of the moon, not in the permanently shadowed regions, on the sunlit surface, in a mid-latitude crater called Clavius. The concentration was much lower than what LCROSS found in Cabeus, about 100 to 400 parts per million, compared to roughly 56,000 parts per million in Cabeus. But the presence of water on the sunlit surface was a surprise. What is it doing there? The sunlit surface of the moon is exposed to ultraviolet radiation and the solar wind. Water molecules on an exposed surface should be destroyed or driven off relatively quickly. One explanation is that the water is constantly being replenished, produced by the solar wind delivering hydrogen that reacts with soil oxygen to make hydroxyl and water. Another is that it is trapped inside glass beads in the regolith, tiny spheres of glass created by micrometeorite impacts, shielded from the surface environment. The truth is probably a combination of factors. The SOFIA discovery reinforced that water on the moon is more widespread and more complex than even the optimistic post-LCROSS picture suggested. The moon is not a watery world, but it is not the bone-dry desert that the Apollo samples suggested either. It is something more nuanced, a world with water locked in cold traps, sprinkled in trace amounts across sunlit surfaces, embedded in minerals, a world where water is present but hard-won. Another major advance in understanding the lunar South Pole came from the Lunar Reconnaissance Orbiter, which has now been in operation for 15 years and continues to return extraordinary science. LRO's Miniature Radio Frequency Instrument, or Mini-RF, has mapped the radar reflectance of the permanently shadowed regions, in detail, far beyond anything Clementine managed. The results show that many of the permanently shadowed craters near the South Pole have elevated circular polarization ratios, which, as we mentioned earlier, is the radar signature associated with ice. Not all of them, interestingly. Some craters are shadowed, but do not show the ice signature. Others show it strongly. The distribution is patchy, which tells scientists something about how the ice got there and how it has evolved over time. The patchy distribution also raises an interesting question. Cabeus was a particularly good target for LCROSS, precisely because the evidence for ice concentration was strong there. But other craters might have different concentrations, different compositions, different depths. The South Pole is not a uniform ice sheet. It is a complex, varied landscape of cold traps, each with their own history and their own character. Future missions will need to map this landscape in much greater detail before large-scale resource extraction becomes practical. You want to know not just that there is water, but where the richest deposits are, how deep they go, what they are mixed with, whether there are contaminants or complications. This is exactly the kind of reconnaissance that precedes any major resource development operation here on Earth, and the same logic applies on the Moon. One of the more poetic aspects of the LCROSS story is what it says about patience and persistence in science. The idea that there might be water ice in permanently shadowed lunar craters was first proposed seriously in the 1960s. For 30-plus years, it was a theoretical possibility that most people in the planetary science community were aware of, but could not confirm. Clementine hinted at it. Lunar prospectors strengthened the hint. But confirmation required a new mission, creative engineering, and a spacecraft willing to sacrifice itself. That is often how science works. The big discoveries rarely come in a single flash of insight. They accumulate over decades. Each mission adds a piece. Each dataset raises new questions and suggests new experiments. The confirmation of water on the Moon was the result of a half-century of observation, theory, and incremental advancement. LCROSS was the moment when enough pieces were in place to deliver the definitive answer. And science is still not done with the Moon. It is far from done. The Chang'e missions from China have been exploring the lunar surface with increasing sophistication. Chang'e 4 landed on the far side of the Moon in 2019, a first in history, and the Yutu-2 rover has been exploring the von Karman crater, returning data that scientists are still analyzing. Chang'e 5 returned a lunar sample in 2020, the first lunar sample brought back to Earth since the Soviet Luna 24 mission in 1976, and those samples are revealing new details about the Moon's volcanic history. China has announced plans for a permanent research station near the lunar South Pole in the 2030s. India's Chandrayaan missions have also made significant contributions. Chandrayaan-1, launched in 2008, carried a NASA instrument called the Moon Mineralogy Mapper, which detected the spectral signature of water and hydroxyl across the lunar surface, adding to the pre-LCROSS picture of a moon that was not entirely dry. Chandrayaan-3 successfully landed near the lunar South Pole in August 2023, making India the fourth country to achieve a soft landing on the Moon and the first to land near the South Pole. Pragyan, the rover, returned data from the surface before the lunar night ended its operation. There is a new space race underway, and the South Pole of the Moon is the prize. The LCROSS discovery is, at least in part, why. Let us take a moment to think about what LCROSS means in a longer historical context, because I think it deserves that framing. Throughout human history, water has determined where civilizations grow. Rivers, lakes, aquifers. Every city on Earth is where it is because of access to water. The first urban settlements in Mesopotamia grew up along the Tigris and Euphrates. Ancient Egypt was the gift of the Nile. The great cities of the world, London, Paris, New York, Cairo, Tokyo, are all on or near major bodies of water. Water is so fundamental to human civilization that we sometimes forget it is a resource at all. It is just there. But it is not just there. It is there because our ancestors settled where it was available. On the moon, there is no river, no lake, no ocean. For most of human history, for the entire history of space exploration up to 1994, we believed there was no water at all. If we were going to live on the moon, we were going to have to bring everything with us, including every drop of water, from the cradle of Earth's gravity well. LCROSS changed that. Suddenly, the moon had a resource, not abundant, not easy to get to, concentrated in specific locations under specific conditions that require careful engineering to exploit. But it is there, and that means the south pole of the moon is like a river valley on a new continent. The first moon cities, if they ever exist, will almost certainly be near the South Pole. Not for the view, not for the temperatures, but because that is where the water is. That is a profound shift in how we think about the moon. It went from a museum, from a beautiful and scientifically interesting, but ultimately inert and resource-poor environment, to a place with potential, a place with something to offer the humans who visit it, a foothold for the deeper exploration of the solar system. And all of it rests on that one sentence. The LCROSS impact revealed that water ice exists in the permanently shadowed regions of the moon. 9 words that changed our understanding of our nearest neighbor. 9 words that made the moon habitable in principle. 9 words that will eventually, probably, lead to the first human settlement beyond Earth. There is something almost philosophical about the mission itself. LCROSS was designed to destroy itself to answer a question. The Centaur upper stage smashed into Cabeus at 2.5 kilometers per second, releasing all of its kinetic energy in an instant, throwing up a plume that the shepherding spacecraft then flew through and observed and measured, before it too crashed into the surface. Neither spacecraft survived. Both were expended in the service of knowledge. And what they found in that brief moment of observation, those 4 minutes and 16 seconds between the Centaur impact and the LCROSS impact, was enough. The instruments,